Hello everyone, welcome. It is my pleasure today to introduce Chang Lu, who is coming to us from UC Berkeley, where he currently is a postdoc working with Don Song on an exciting family of combinations from machine learning, deep learning technologies, and programming language technologies. He's done several incredible contributions to the program analysis and program synthesis field over the past couple of years, which he'll tell us about, and also to the general area of security, from security in traditional sense for programming languages field, which he has been working on during his PhD at University of Maryland, College Park, as well as security of machine learning systems, new methods of protecting them from adversarial attacks and whatnot. And without further ado, let's pass it to Chang.
Yeah, thank you very much, Alex, for the introduction. So today I'm very happy to be here to share with you my research on neural representations for program analysis and synthesis. So I think because we have a lot of time, feel free to interrupt me for any questions during my talk. So, okay. So we know that program analysis has been studied for many, many years. It dates back to last century, even from the very beginning of the modern computer system. So there are a lot of techniques developed during the past several decades, right? From the very basic compilation technique to more advanced data analysis technique, and to the more recently interesting data synthesis technique, right? So if we take a higher level look at these techniques, we found that most of them are based on some rules, deduction rules or the type system rules, to solve certain kind of optimization problems. And nowadays, in the recent years, we have a new class of tools that is called deep learning that can solve optimization problems very efficiently and very effectively. So our question is, can we leverage deep learning to build a better program analysis or the program synthesis tool, right? So let's step back from this perspective. So let's see if we want to apply deep learning to program analysis. Then what do we need to do? Actually, the main challenge is that the two class of problems are actually in the different lengths. On the one hand, programs are in the discrete length. Every objects are discrete. And on the other hand, deep learning is basically optimization tools in the continuous length, right? So there is a big gap between the two, which prevent us to apply deep learning technologies to these program analysis problems, right? So we have two problems here. So the first problem is, so if the gap is so big, then why do we even want to use deep learning for handling programs? And the second is, how can we bridge the gap to make this really happen? So today, what I will talk about is on neural program representation that can serve as this bridge to convert the discrete optimization problem into its neural representation, so that the hammer from deep learning community can be leveraged to solve the problems efficiently. And also throughout my talk, I also introduce several of my work that shows the necessity of this kind of combination that will enable something that cannot happen before, right? So throughout the rest of my talk, I will introduce the two classes of my work. One is in code analysis, actually in the binary format, and the second class is in the neural program synthesis. And in the end, I will also briefly mention some of my other efforts in the larger field of deep learning, right? So, okay. So let's start from this binary code analysis problem. So, right, I need to give you a little introduction about what I'm doing. So I'm basically a security researcher. So one of the security challenges in today is, how do we handle the security of these IoT devices, right? So they could link to all the different digital life of your life. For example, it can link to your phone, your home equipment, your cars, or even other. There are a lot of things on that. So there is a projection that in 2020 there will be over 50 billion different IoT devices available on the market. So their security issues are very important. And then we need to understand when these IoT devices are under attack and when they are safe to use, right? So if we take a look at this architecture, which is a typical firmware on top of operating IoT device. So there's one component in here which contains the libraries. So typically, there are a lot of libraries operating the entire IoT device, but actually there is one very important library that is the OpenSSL, which allows the different IoT devices or the servers to communicate with each other over the internet or other kind of network through a secure channel, right? So OpenSSL is a standard implementation of the TLS protocol, which simply enables you to communicate your very sensitive data in a secure way, right? But actually, we found that although most of these IoT devices will employ the OpenSSL in their development of the firmware, but we found that OpenSSL is always disclosed with many different vulnerabilities, right, which make this kind of employment very suspicious and very vulnerable. So one of the big events that happened 4 years ago, actually in 2014, is this called the Heartbleed vulnerability. So this is a very simple implementation problems when checking the boundary of the array that will allow the attacker to probe in the device's memory up to 64 kilobytes. And then so this simple vulnerability affects hundreds of different websites, including those famous ones like Pinterest and GitHub, right? So, and also a lot of the IoT devices are also affected by this simple vulnerability. So our problem is, okay, this kind of new vulnerability is disclosed, for example, in today. Then how can we check whether my device or some other devices in my home are affected or not, right? So then we have this vulnerability detection problem. That is, on the one hand, we have the sample code, maybe in binary, of the vulnerability code sample, right? And on the other hand, we have a database of all different firmware images operating the IoT devices of hundreds or thousands of different IoT devices, right? So we want to check whether the vulnerable copies appear in the binary code in our database. But there is a problem that the binary code in our database could be written on different architectures. Some of them are in x86, some of them are in ARMs and MIPS. So actually, we want to check for this vulnerability detection in different architectures, right? So what is so far everyone is with me? Any questions so far? Okay, that's good. Okay, so then how can we do that? There is a very simple solution. We can scan through all the firmware images on the right-hand side to check whether the vulnerable code sample is similar to the binary code in our database, right? And then if it is not similar, then we know that probably the binary code is not affected by the vulnerability that we just disclosed, right? If it is, on the other hand, if it is similar to some code piece in the binary code, then we know that potentially the code piece in the database is vulnerable, right? Then we can scan through all the different firmware images in the database to check which one is vulnerable and which one is not, right? So, okay, this procedure is very simple, but we observe that there is a key functionality to check whether the vulnerability is similar to the code piece on the right-hand side. Right, this part is the key part that I have not explained, and essentially this is the key problem that we want to solve here. Actually, there's one more caveat is that I have mentioned multiple times. Yes, go ahead.
So when you say similar, like how much code is similar?
Yeah, that's a very good question. I will show you in the next few slides. Okay. Right, don't worry. Right, actually, before we go to there, so we want to mention that there is a caveat that is in the database, the code is in different architectures. So the encoding are totally different. So that if you look at the byte level, so basically all of them are quite different from each other. but we want to check whether they are semantically equivalent or serving the same functionality as in the vulnerable code pieces, right? Okay, so here is the thing. So what my work is that we develop a neural network to handle this problem. But before that, so let's wait a minute. Let's think about a larger question first. So as I have mentioned multiple times, why do we even want to apply this deep learning, right? Because program analysis is totally in the discrete world. But why do we want to use this continuous space optimization tool? So I will give you one example, which also is an example to explain what does it mean by similar. So actually, we found whether it's similar or not is a very hard problem to even define that. So let's consider these two code pieces. So both of them are implementing a functionality that copies a string within array B into array A, right? So the most part of the two programs are identical, but the bottom one has one line. So what it does is that we all know that in the C encoding of a string, all the strings are ended with a 0, right? So in the bottom code, it will write a 0 at the end, but in the top code, it forgets to write, right? So we consider the different co-similarity scenario. In the plagiarism detection, we know these two code pieces are similar because the majority of the code are identical. We can safely assume that they are copied from each other, right? But on the other hand, if we consider vulnerability detection, they should not be considered as similar because the bottom one has already fixed the end with 0 vulnerability, but the top one has this vulnerability. Therefore, in the vulnerability detection problem, these two code pieces should not be considered similar. Therefore, so using this example, I just show you the reason why we want to use a machine learning approach to handle that is because any single manually designed heuristic, I should say deterministic heuristic, cannot work for both application scenarios at the same time. Therefore, for different applications, we need to develop different heuristics to handle them, right? But using deep learning or machine learning in general, we can solve this issue in an elegant way. And I will show you how. Okay. So before we go in there, let's take a look at this problem from a very high level. How we can solve that using machine learning. So from this figure, this is a very simple figure. We have the firmware binary code on the one hand side, and we have the vulnerability on the other hand side, right? We simply run an embedding function, pi, that will convert them into two embeddings. One is V1. Yeah, go ahead.
Do you assume that the compiler that compiled the firmware files is the same?
No.
There's no
right. We just crawl them from the WAL, so they are compiled using all different sorts of compilers with all different fancy optimizers within the IoT device company. So the binary code are totally different, right?
So one compiler that might change the order of instructions, for example,
yeah,
would look to what you just described like a dissimilarity.
Right? Right. So if we just right, I will also show this example. So actually, if you just change the order of two independent instructions, they do not change the semantics of the code. Right.
Okay, yeah, keep going.
Right. Yeah, good question. So I will just explain them. Okay. So let's still talking about this whole picture. So we can convert both of them into the embedding vectors, V1 and V2. So to check whether they are similar or not, we can simply employ the cosine similarity function. And there are also other similarity metrics that we can employ here. But basically, after the embedding is computed, we can employ numerous techniques to handle that.
Can you say what the input for those?
Yeah,
so
the input.
What's the input for a vulnerability?
Right, that's very.
The binary code somehow? Or?
Yeah, that's the binary code of the. So typically in the experiment setting, we did this. So we can grab the change log, and then we can locate which file is changed. Then we can compile that into the binary code. Then we know what the vulnerable code sample looks like. Right.
So it's a sample of a vulnerable code before it has been fixed.
Right.
Into binary.
Right. Exactly.
Okay.
Right. Good question. Okay. So
what if like there are a lot of how big is
the input. Like if I'm imagining there's a delta that's really large,
Right.
You feed in a very large binary, but
Right. That's a very good point. So actually in the experiment that we have done, so most of the binary code are not that big. Most of the changes are not that big. So typically they are within certain small number of functions. So, but we only need to take care of one function as the signature to do all this kind of work. Right. Right.
so if you change something inside of a function and the binary code for that function changes,
Yeah, it will
you feed
change.
in the like some delta of some sort, or you feed in the entire function.
We feed the entire function to check whether it is similar or not. Right. Because it is also very hard to figure out the delta, even when they are in different platforms, especially, right? So, okay, then how can we obtain this pi? The answer is we just use deep learning. So, I believe most of you here should be familiar with this kind of formalization, but I want to briefly mention that deep learning or I should say supervised learning is a way to kind of approximate this function pi when you are giving a list of input-output pairs, which we call the training data x and y. So the solution is that we can simply approximate this function pi with a parameterized model, and then we can simply minimize the loss with respect to these parameters to get the solution. So here we have two key questions to answer. The first question is how can we construct this data set? And the second answer is what kind of model architecture should we use, right? So in the following, I just answer them one by one. For the data set, a naive idea is very simple. You just have the binary. Can we simply construct the embedding for them, right? And then we can train the entire network in a very straightforward way. But actually, this naive idea, of course, doesn't work because so far we don't have any embedding for any objects, right? Even in those traditional fields like image, speech, or language, we don't have this embedding supervision. So this kind of supervision is very hard to get. What we do is that we build a wrapper function, which is actually a CME network, to wrap the two. So that's rather than giving a supervision on every single binary code, we give supervision on a pair of binary code and whether they are similar or not, right? So this wrapper function is simply the entire function that we want to compute. What is the? Am I standing in front of the? Okay, it works. Okay, good. So it simply computes the entire function that we want to compute for the code similarity detection problem. Maybe it's the connection not very well, but hope it will work. Okay. So then, okay. So let's say how can we construct it? Yeah, go ahead.
I didn't quite understand. Why not you just do the supervised learning approach? You know that some code are kind of vulnerable, so or you just learn fx theta this embedding, and then for vulnerable code it's vulnerable, so its label is 1, and for normal code it's 0, so it's
right, because we don't have right. That's a good question. So actually we don't have we have several problems. The first one is that we don't have this strong supervision in our data set. So typically, if we want to label something vulnerable, that is much simpler because we can simply extract the code, the CVE file from the website. But if we want to say some code is not vulnerable, it is very, very hard because you don't know whether it's really vulnerable or it's just not discovered, right? So and also we suffer another problem is that the vulnerable code samples are relatively much fewer than the benign one, right? So in this case we will have a very skewed data set we don't have a balanced distribution, so that training the data in this way is not very effective. Yes, go ahead.
I just have a basic question. Are you modeling the code as a sequence or as a graph? What are you
That's exactly the next problem that I want to show. What model architecture do I use?
Oh, I see.
Right.
So when you say embedding, you're not okay.
That's a numerous vector. Embedding is just a numerical vector.
Okay.
Right, and then I will show how that is actually computed in in the next part of the of this work. Right. So okay, so let's say we have this wrapper function. It is very easy to construct a balanced data set with positive and negative samples. For example, we can have a source function. It is very easy. We just crawl SourceForge or GitHub. There are a bunch of them. We can compile them using different compilers into different architectures and using different optimization levels, right? Then we can have a lot of different binary code. They are totally different in their encoding of the bytes, but they all correspond to the same source function. Then we know that they must be similar to each other. Then it's very simple. We just label them as similar. On the other hand, we can have two different source code, and then we can use the same way to compile to get the binary functions compiled from different source code. Then we know that they are dissimilar. So here we kind of have an intuition that the binary functions compiled from the same function are similar. This is for sure. But on the dissimilar one, we simply treat different source functions as not similar, right? Yeah.
How do you decide which functions to put into your data set?
Right, that is also a good question. So actually, what we did is that we just get OpenSSL, several versions of OpenSSL, and then we compile them to get the corresponding binary functions, and then we split the data into training, validation, and test set randomly so that they do not overlap in any sense. Right. This is the way how we decide the source code.
Do you have confidence that your network trained on OpenSSL will generalize to other?
Right. That is something that we evaluate. Right. That is something we evaluate. Right. So, okay. Right, that is a very good question. But actually, if we consider I will talk about this in a later part. So let's just finish this problem about. Okay, so let's move on to this problem. We have these two different. We have two different pieces of code which look similar and not similar at the same time. So how can we incorporate that into this framework? It is very simple. We can incorporate human expert to provide the label to say that whether they are similar or they are not similar. And in this way, we can simply incorporate this kind of human label data into the training set so that everything else will be the same. We don't need to develop new training algorithms or things like that. So, and then we can apply to the application scenarios that we want. Right. So, yes.
Do you need to give higher weights to human labels?
Yes, exactly. We have a higher sample rate because it is much smaller than the automatically generated data. Right. So that's a very good point. Yes.
Where do you get the application dependence? I mean, you just made me make a decision on those two pieces of code. Do I say dissimilar for vulnerability and similar for plagiarism? Is that?
Yeah, that's right.
So I have another column called application, and then I get to define similarity as a function of application? Is that
yeah, actually, right. This is a good question about the concrete way how this can be applied into the scenario. So basically, we call this way to generate the data called the application independent data set, which is huge, and that is the majority of the data. And for this for this data set, we don't have the additional column of which application it is. So basically, all the application will share this part. And for the second part, which is much more expensive to acquire, which requires label experts to label them, we only have a few of them, a very small set of them, so that for the concrete applications, rather than having a big data set containing all the different training set, all the training data, we build one training data for one application itself, so that we don't have explicitly labeled that which application it is, but typically this part of the data is different for every different application. Yes.
How big are the code fragments you showed to the humans?
The code fragment to the human is varies a lot. So in our experiment, we show about several tens to several hundreds of binary instructions. So we look at binary. Right. So that is how human experts can gather data. So this is why I said that is very expensive. Human experts really need to use the dissembler to look at the code. Sorry.
Are they at least disassembled when the humans look at them?
Exactly. They are not binary. They are not true binary. They are assembly language. Yes. Yeah.
So how many instructions?
Oh, right. As I mentioned, tens of instructions or hundreds of instructions. Right.
Okay.
Right. We typically don't handle millions of binary codes.
So what was the insight that made you think that that was the right amount to detect similar versus dissimilar?
Oh, right. So the boundary. Right. That's a good question. So the boundary we decide is not on the code that we need to look at, but actually the boundary is decided by the function boundary. So we just take all the instructions from one single function and then look at them to compare them whether they are similar or not. Right. Right. So
if the function was too big, you wouldn't show it to the human. Is that right?
Right. That will cost more expense. That is more expensive
so
to
would
get
that
the
limit
data.
the effectiveness of your approach on a larger function? How to
That is a very good point. So very luckily in my experiment, I didn't involve that large. So we have graph with over 1,000 number of nodes, but we didn't inspect them manually. Right. So I'm sorry. So that guy is first.
So, what expertise do you expect the labeler to have for different applications?
Right.
Different types of applications require different.
Sure. Yeah. Right. So in this particular experiments in this particular application that we do experiments, we expect the human expert have the enough expertise to do all the disassembling and then inspecting the assembly code, this kind of jobs. And right, so actually it can be tricky, but it's actually not that hard. So I am serving as the expertise, right? And I learned from disassembling them and look at the binary code from scratch, and then I could handle them after 1 day of training or something like that. Right? It can be very tricky, but it's.
Of this, like in the malware case, you need to know the nature of the attack.
Right.
Exactly. To be able to determine that this is a vulnerability, and this is, whereas a plagiarism, you might not need a subject matter expert in that. Okay.
Exactly. So this is simply repeat my opinion on this. It is total application dependent, and different applications they have different requirements. So.
Yeah, still have a very basic question, though. I mean, it's well known, like in anything like SAT or programs, there are many equivalent programs you get by renaming. So how do you even address sort of basic issues like names of registers and memory locations?
Yeah, that's a very good question. So actually, as I mentioned in the last several slides, that I'm not handling that level of semantic equivalence, which is very, very hard. Basically, you know that it's of course Turing complete, right? So we cannot handle that. But actually, for this particular vulnerability detection, we are lucky because we only need to handle whether binary codes are compiled from one version of the source code. So this is why our problem, our technique is solving some problem that is actually simpler than the generic decision problem.
I still don't understand, how do you model a program? What's your model of a program?
Right. So basically,
you present to the machine learning.
Right. So typically, I think when you say modeling a program, basically you want to, what you mean is that you want to give the ground truth of whether two code pieces are similar or not.
What I mean is, what do you do to encode a program for presentation as a training set to your learning algorithm? Very basic question.
Right, that is the thing that I'm going to talk in the next couple slides. I mentioned.
I'm sorry. I expect like in the way I do program analysis, this is always the first question.
Sure. I'm sorry. I should.
It's coming very late. So.
Right. Sorry. I should move the second. I should move the second question first. Okay. But I apologize, but it will come first.
So it's still coming. It's still coming.
Yeah, it's coming. Yeah, go ahead.
Okay, so it's not clear to me why you need a human expert. So you have these two versions, right? You have SSL with and without heartbleed. You know what functions they occur in. So you can be like, okay, this is the version where it had the vulnerability. This is where it didn't. Those that have the vulnerability are all similar to each other. Those that didn't are all similar to each other. So what value does the human annotator provide?
Oh, exactly. This example shows you the whether two code pieces are vulnerable or not, are similar or not, are application dependent. So this is the only thing that human needs to tell the learning system. What do I think is similar and what do I think is not similar? Right. These are just some ambiguous case that machine cannot simply figure that themselves. Is that answering your question? we can talk about that offline.
So
yes.
For instance, did you have cases like this where I'd imagine you could see on the left is the code before we fix the vulnerability, on the right the code after we fix the vulnerability?
Yeah. We have this very hard cases.
So you had cases where both of these are compiled to very similar binary.
Right.
So you need to explicitly distinguish them.
Right. We indeed have these kind of very hard cases in the evaluation. I'm not sure if I show that in the following, but we indeed have these hard cases. Okay. So, are we all good so far? Okay, good. So let's move on to the question that that we are all very interested in. How do we model the code, right? So typically, a very naive way to consider that is that a binary code is simply a sequence of bytes. So the very naive way is to simply use an LSTM to generate the embedding using the hidden states at the end of the LSTM, right? But so we consider whether there are any problems with this kind of encoding. So actually there are a few, right? So one problem is about the sequence ordering problem. So we all know that LSTM is very sensitive. The LSTM encoding is very sensitive to the order, which I will show in the very end that there is a problem called order matters problem with LSTM, right? So, but on the other hand, we also know that for these two code pieces, they are actually identical, because A and B, two variables, are independent to each other. Whether you assign one first or the other one first, it doesn't really matter. So both of them, after executing both of them, A and B will both have value 1, right? So the order in this case doesn't really matter, but if we simply use LSTM, so I will treat them differently. So this is one case why LSTM is not so doesn't make so much sense. And there's another case is that if we simply consider this conditioning program, I don't show you the concrete case, but actually it is very obvious. Actually, only one block will be executed in every single run. So actually, the two blocks doesn't have much dependency on each other, right? So, but actually, if we serialize them down into one binary sequence, then there will be dependence, right? And then which one, no matter which one comes first, that one will have some the other one will have dependence on that, and so the entire encoding will be quite different, and then quite sensitive to the ordering of this serialization, right? So we think that LSTM might not be the best choice in this case. So what we do in our work is that we convert that into a so-called attributed control flow graph to answer your question. So basically, we can extract the control flow graph using a disassembler from the binary code. And then on the graph, every single node corresponds to a simple code block, right, which we call basic block. And for each basic block, we will compute a back-and-forth embedding of several of the instructions, and then based on the statistic of these instructions. So here I will not show them. I not discuss them in a very detailed way, but actually these are some heuristics that have been used in previous work. Okay, so after we get to the attribute, yes?
So the control flow graph, you have a graph, okay, oh, you're going to talk about it. I was going to say, you still have a graph, right? You have to linearize it or do something with it.
Right, exactly. So we want to compute the embedding for the attribute graph, but we don't have to serialize that. So actually what we use is this work. It's a structure called structure to vec. So I'm sorry, that's a ICML paper. So basically what it does is that it converts a graph into an embedding. So right after you take the photo, I will show you the concrete architecture. It looks like it works in the following way. So initially every single node will have an initial embedding, which is computed in the way that I mentioned by computing some back of words embedding or something and so on. And then I will iteratively update this embedding using this kind of information propagation kind of style. So for every single iteration, the embedding on one vertex will be propagated onto other vertices along with these edges. And then on the other, when the information is propagated, there will be some cell. So actually, in our implementation, it should be a CM cell to update the embedding of every single node. And then in the very end, after t iterations, where t is a hyperparameter, we get the embedding for every single node, and then we simply sum them up. And then through a fine transformation, we will get the final embedding for the original graph. So in this way, we know that information only propagates through these edges, which capture the control flow dependency, but it doesn't have to serialize everything together, right? So everyone with me so far? Yes.
So in the from the first to the second layer, you're encoding the directional links in the graph.
Every single iteration, it will encode these edges of the graph. But in the first level, the embedding for here is computed directly from what we call attributes. That is this A in the ACFG, right? Which is computed using some heuristics to compute the back of words embedding, right? Yes?
So the arrows in your directed graph, is that just a single weight plus bias transform?
The edges are just some kind of control flow dependency, like when you have a jump, then you have one link from one basic block to the other.
In the neural network.
In the neural network.
When you propagate an embedding in a single iteration, is that a feed-forward layer? Or?
Oh, right, that's a good question. So we have multiple. So let's just consider this x3, right? It has two incoming edges, right? x1 and x2. We will have the embedding for them, and then we can sum them up, right? Because every single node will have different number of incoming edges.
So it's a summation.
Right. We do a summation, and then we will. There's another slide, but I'm very sorry I didn't include that in here. It will go through a neural network with the embedding on here and the original attributes embedding on here, so that and as the output is the new embedding for the next iteration, right? So I think I should include the concrete network, but I'm very sorry I don't have that for now.
Is T a hyperparameter?
Right, T is a hyperparameter. That we try different hyperparameter, but we found it doesn't matter that much. So typically T, we range T from 2 to 5. Actually, 2 works very well already. So it says that right. So actually propagation doesn't have to be that long. Yeah.
So what are the parameters in this network? Here I saw in the last layer you have this W2.
Right, exactly. Right. Good point. So when we aggregate these embeddings together onto this node, we will run through a neural network, and then that network has many different parameters inside. So, but as I mentioned, I don't show that here. Right.
So I was trying to understand, like, there's no parameter in in the whole propagation structure, and there's only that W2 at the end.
There are parameters in the propagation.
They are. During propagation, say run through a neural network, which has a lot of parameters to train.
Like new one is obtained from a neural network applied on the sum of new one and
right.
Yeah, okay. So the input edges.
Right, exactly.
Layer.
Right. So here is a little bit unillustrative, but actually, the computation of this is depending on these different values, and then I will run through a neural network to compute the final output.
So each arrow in this graph is associated with its own neural network.
Right.
Yeah.
Kind of, yeah.
Yes, and this is the whole set of parameters that you train for iteration.
Sure. Yeah, you can understand that.
So there's a particular neural network for each node in the graph, that take care of the processing the inputs from its input nodes.
Sorry, I don't get you.
So is it a case that is there a different neural network for each node in the graph?
Oh, they are all the same and they share the same weights.
Okay, so the same.
Right.
Right. And the network just takes the sum of the inputs from the input nodes, passes through the network, and then.
Right.
Is that it? Does not interact with the embedding original in the node already. So you have
no. As I illustrate here, it indeed interacts with the original embedding.
So is that a sum? It's
not. No, it's not a sum. The summation happens here, and then there will be a feed-forward network running in.
So you concatenate those two vectors.
You can consider that it's a little bit more complicated, but you get the intuition, right?
For different iterations, do you share the weights on the edges?
Yeah, that's a very good question. You can train them using different weights. You can also share the same weights. So actually, there is no difference in performance. Right.
I'm sort of losing the big picture here. So at a high level, if you want to compare programs, you can do it syntactically, you can do it semantically, very roughly. You've encoded some semantic attribute, which is this program statement comes before this other. But the other things you will want to encode are, for example, register names, memory locations. So is it a goal of yours to also model data flow, or do you want the machine learning to have to learn data flow? I mean, because again, your choice of representation sort of is your seed from which the learning starts. And so I see that you're modeling at a high level the control flow graph. What else are you presenting, and what are you, at a high level, what do you want the DNN to do for you? I know it's hard to say exactly what it will learn, but do you want it to interpret your program?
No. So let's say we simply want to do better than previous approach. And then what our previous approach is doing is do graph matching based on the control flow. They do graph matching.
On what sort of graph?
On control flow graph.
On control flow.
Right. So they have control flow. Right. So that is all the previous approach.
And what do they do with respect to abstracting over variable names?
Right. So variable
because you could use SSA form instead of control flow graphs. Right.
Exactly.
Data flow. You could use a data flow representation of a function.
Right. So in the variant level, we only have registers.
Okay.
Right. So actually, we abstract away all those different variables in the back of word embedding. Okay. We count several statistics, like how many constants do we use, how many different registers do we use.
You're not going to preserve semantics here. You were going to
not full. We only
the program.
Right. Exactly.
With your bag of words. Okay, that's clear. So you're not hoping that the DNN is going to execute something for you.
Right. Exactly.
At any level.
Right.
Your goal is to do pattern recognition, which is more general or perhaps better than these previous approaches, which were graph-based. Okay, I get that.
Okay, good question to make sure everyone has already been clarified. Okay, yeah. So you want to answer?
No. Actually, I think we should move on.
Okay, let's move on.
The second half of the talk.
Okay, yeah. So let me just show you some results. So this is actually illustrate the embedding on the 2D space using t-SNE. So we observe that the binary functions compiled from the same source code are clustered together, and from different functions they are separated apart. So which illustrate that this is very effective. And also I show you here the ROC curve, which is much better than the previous approach, which is just a graph matching based approach. That I don't want to spend too much time on this because I want to move on to the second part. Okay. So, and also what is worth to mention is that our approach is very, very efficient in terms of both training time and testing time. So for the training time for the previous approach, it will take more than a week. But for our approach, it takes less than 30 minutes to train a very effective model. So we can retrain them multiple times during real development. And for the serving time, so previous approach, because they do graph matching, yes?
So I'm sorry, the previous approach, why does it do training? Is it a
right, that is a good question. So it's a bit tricky to answer. So what they really do is that they try to find several several representative graphs from the large, they have a large training set. They want to find several graphs from that large data set. And then when they have a new graph coming in, they compute the similarity between every single graph in the representative set. And then they can, so let's say there are 10 graphs, then you have 10 different similarity scores. Then these 10 scores will become a new, embedding vector of the newly comped program, binary code. Right. So and then in this way, then following that, they will do the similarity comparison between the two embeddings. So that is why they need the training time, because they want to construct that large set of.
So they have an n-squared problem with the size of the number of samples.
Right. Similar to that, and then there are billions of functions. So they have a hard time to really get this set. Right, and also because previous approach requires to run this graph matching on all these graphs, so it is very slow. It runs from a few seconds to a few minutes, but our thing will only require a few milliseconds. Right, so it is 3 to 4 orders of magnitude faster. So okay, so let's stop here for the first work. So basically, the thing I want to point out is that in certain kinds of program analysis tasks, deep learning can be more efficient and more effective at the same time. Therefore, we should consider that program analysis as a novel application domain for the deep learning techniques. Okay, so in the following, I want to talk about the program synthesis part. I hope I will have enough time. So I have done several works in this domain. So we synthesize programs from different specifications. We synthesize. So the work that I will talk about is from input-output examples. But we also do. I will also, if I have time, then I will also briefly talk about synthesized program from natural language descriptions. And we are also working on to translate program from one language into another. Right. So, okay, let's start from the first. So input, I think everybody here should have already been very familiar with input-output program synthesis, but I just want to complete this slide. So basically, we have a set of input and outputs, and then we want to give a new input, then we want to know what is the answer. So we have a guess, which might be that we just reverse the function here, and then, okay, then we can use that function to answer the new question. Right, so here the key ingredients is that we have the input-output examples, which can also be called demonstrations, and we want to synthesize some program which will be run on some test examples. Okay, so there are a fruitful of results coming into the field, most of it coming from here, which is very excited. So for example, for this flash field functionality already implemented in Excel, and this carrier dataset is newly released dataset from Microsoft as well, and some of you are working on this. Right. So, but there is one way. So if we look at the program complexity of the programs to be synthesized into this domain, then we found that it is not that complicated. For example, for the robust field paper, we take a closer look at the DSL algorithm, we found that basically the program we can synthesize is a concatenation of up to 10 different constructors, each of which is a combination of a recursion of almost 2 levels of string operators, right? So, and there's no control flow at all for the robust field problem. And also, if we take a look at the Carroll problem, so we basically compute the statistics for the Carroll dataset, we found that for this kind of control flow, almost the majority of them don't have any control flow at all. And then even though for those that indeed have control flow, so over 90% of them will only have at most 2 control flow operators, right, inside. So here's the problem that we want to ask a more high-level question. So if we want to push forward the frontier of this program synthesis, we want to synthesize more complex program. Here I put them into quotes because here complexity is a very, very, very vague notion that we simply count the number of branches. But so if we want to synthesize more complex program, then we'll ask our 2 questions. One is, what are the key challenges that we will face during this path? And the other is, what are the key techniques that we should develop to finally tackle them, right? So to answer them, we introduce, toward answering them, so we cannot answer that right now, but we are moving along that path. So we introduce another problem called parsing problem. So it is very standard. I think most of you I should say all of you are familiar with this. So we have an input, which is a sequence of tokens, and then we want to convert them into a parse tree. So this is a very typical problem that has been studied for many decades. And the key challenge here is that we want to study this problem when the grammar is unknown, right? So when the grammar is unknown, there are several technical difficulties which make this problem very, very challenging, right? And okay, so to study this problem, we synthesize, we manually create several benchmarks, and we found that the key functionality of a parser for a context-free grammar is basically an automata, right? So and then to implement an automata is a bunch of if-then rules, right? So typically, we calculate the statistics of the automata that we created. We found most of them contain many different branches, so that which is far more complex than the existing programs that we synthesized so far. Okay, so this is a very vague way to characterize what do I mean by complexity. It is not rigorous at all, but I just give you an intuition about what I'm talking about. So okay, so because this problem is more complex in the terms of that it contains more control flows, so we consider what are the solutions that we can have to deal with them. The very naive solution I have already mentioned in the last work. This is basically a function approximation problem, right? We simply want to find a function that can translate the input into the output, right? So what we can do is why don't we just build a neural network and then train that over the input-output pairs? And actually, this is indeed a solution released a couple of years ago, and this is a very famous work. But actually, if we ask the question, does it generalize to longer inputs? And then our evaluation will show that this doesn't generalize, right? So, and then this is a very fundamental constraint in the current sequence-to-sequence neural network, is that it simply doesn't generalize to longer inputs, right? So, and then in the recent year, there's another line of research that is studying these kind of neural programs. What it does is that there's an underlying machine implements the functionalities for you and provides several APIs, right? And then given an input, the neural program will kind of compute based on the input and the state of the machine, and then predict instructions to be executed by the machine. And then machine will be executed and state will be updated, and then the state will be transferred back to the neural program, and the neural program will predict the next instruction. And then this procedure will go on until the last instruction is executed, and the machine can compute an output, right? So this is a hybrid approach that we can have a neural network to operate the machine, but the machine itself is a discrete object. And there have been several works implementing this idea. So I'm sorry, I should put that a little bit up. But basically, this line of work called NPI actually is an implementation of this model, right? And there have been, so another work from our group, which is the Best Paper Award, actually shows that it is possible to achieve full generalization or perfect generalization to arbitrarily long inputs using this approach and recursion. But actually, there's an important caveat is that to train this kind of neural network model, you need to have strong supervision on every single instructions in these execution traces, right? So it is very hard to get rid of them. So, okay, let's take a step back. So take a look at what we have been talking about so far. So in the traditional program synthesis world, we have this search-based program synthesis using SMT solvers or some other things. All of them are basically a search procedure. But we found that it is the programs that have been synthesized can generalize well to arbitrary setting, but it is very hard to synthesize because the search procedure is typically very expensive. And on the other hand, we have this end-to-end neural network approach, which is basically very easy to train due to the popularity of this gradient descent style optimization approach. But it is very hard to generalize, as I have mentioned. They simply cannot generalize to longer inputs. So the philosophy here is that we develop a hybrid approach to combine the benefits of the two. So we train a neural network operating a non-differentiable machine. So the non-differentiable machine part can provide us the generalizability. So the only problem we need to figure out is how can we train the neural program very efficiently without relying on the execution traces, right? So, and this is the key problem that we solved so far, that we solve in this work. So let's repeat. We have two goals. One is the generalizability, and the other is how to train that, right? So here's the roadmap. We do this two part of work in combine to solve this problem, exactly corresponding to every single problem that I mentioned above. So first, we designed this machine, LL machine, which allows a neural program to generalize to arbitrary long inputs. And on the other hand, we develop a reinforcement learning-based approach, which allow you to train the neural program without the supervision on the execution traces. Right. Okay, so let me explain them one by one very quickly because we don't have a lot of time. So I hope that the explanation can be easy to understand, but if you don't understand, then just pause me. Okay, so our machine, so when we describe a machine, we need to describe two objects. One is the state, what kind of the content is stored in the machine, what is the memory model or something like that. And the other is what kind of APIs that they provide. We call them instructions. So for the state, we provide the input stream, which is basically a token sequence. And we also provide a stack, which I will demonstrate how it is used. On the instruction set, we will have four instructions, which can be classified into two categories. The first two instructions are shift and reduce, which are the basic functionality to implement a shift-reduce parser. And on the other hand, we have call and reduce instructions, which are basically the functionalities to implement this stack-based recursion procedure, so that you can actually train the neural program to generalize to arbitrarily long input. Okay, so now I want to give you a long demo, but I want to do that real quick. So for example, on the left-hand side, we have this x plus y. We want to parse that into the parse tree. So what do? So we first execute a shift, then this x is moved to the top frame of the stack, and then we will do a reduce ID1. So this instruction is a little bit complicated. So what it does is that it will construct a parse tree there. So the ID arguments, so ID and 1 are the two arguments to the reduce instruction. ID argument means that the root of the tree is ID. And 1 means that, okay, here is a list. 1 means that there is only one child. First, because the length of this argument list is 1. But if we take a step back, so we take a look at the top frame of the stack. 1 indicates the first element in the entire frame will be converted into the child, the only one child under ID. Right. This is how this reduce works. Okay. After that, we know that okay, the top frame has become into this one tree, which we have been reduced. Okay, and then next we will shift this plus into the top frame, and then we will do a call. So I will explain why we need to do a call in a very right. So later, but after we do a call, we generate a new frame, and then so the frame pointer moves up, and then this is because we want to create a subtree for y itself, without affecting all the other elements that have already been done in the stack. So by doing this call, we simply create a new frame to do this operation for the substring. Okay, and then we still do a shift, and then we still do a reduce, which are basically identical to that x, and then we create the subtree on the right-hand side. Okay, and then we will do a return, which basically pop up the top frame, and then move that back to one frame deeper in the stack. Right, and then right now the top frame contains ID plus ID, which we want to construct an add operator on top. So we will issue this instruction, which means that we will create a tree whose root is add, and it will have two child, 1 and 3, which means that okay, if you take a look at the top frame, which contains 3 tokens actually, the first is ID and the third is also ID. This means that the two children of this add is this ID, which is this ID, and the third ID is this ID, right? So after that, 1 minute. So after that, we will get this, right? Okay, your question.
Are the rules of the grammar embedded in the machine?
Yeah, the rules of the grammar is embedded in the machine.
So you're not learning a general grammar, you're learning a very specific grammar.
Right, specific grammar due to the input-output pairs.
Right.
Right. Good point.
So is the design of this machine a contribution, and did you make it?
I will say this machine is new, so it contains novelty. But whether it is a contribution, we don't claim that as a contribution because so far we do not know whether it can be used in other settings as well. So far, so we hope it can.
Could you think of the machine design as a hyperparameter to the learning?
That's a good point. I think you could say that from a very abstract way.
So there's no tuning parameters in this version. I think
there are a lot, but there are the details because I don't have a lot of time left, so I want to move on so that I can make the main message coming across. Okay. So this is how we generate the parse tree using the machine. So if we want to step back and then take a look at this procedure, this is why we use stack to model the state of the machine, because we can create a new frame on top of the stack so that we can handle the sub-expression explicitly without affecting all other components in the finally generated parse tree. So then this is also the key message. Reduce only handles the elements in the top of the stack, which why it makes it possible to train is because therefore the neural network only needs to learn how to handle the top of the stack as well. So it doesn't need to worry about any elements deeper in the stack. Therefore it can handle arbitrarily deep stack as well, which correspond to arbitrarily long input. So this is the key to make the entire solution generalizable, right? So, okay, so I will move on. So here is everything that I put all the animations in one figure. You don't need to worry about the detail, but you can take a look. But typically, I highlight this decision that we need to make by the parsing machine. So actually, we have the input and we have the output. We need to make all the intermediate decision. What we could do is that we could build a neural parsing program using an ISTM. So we all know that the decision is made. The decision is made based on the stack top and the next input token, and then we will run ISTM to predict the instruction and the argument separately, so that they will be combined, supplied to the machine to really execute that. Okay, so actually the neural parsing program part is very easy. The hard part is how to train that, because the thing is that we only have the input and output pair. We don't have any intermediate. We don't have any supervision on the intermediate execution traces. Then how can we train that? The idea is to use reinforcement learning. The basic intuition is very straightforward. So we simply we use the neural parsing program as the policy network, and then follow the policy to generate different kind of execution traces. So if the result is wrong, then we penalize every step in the trace. We avoid doing them in the future. And if we lead to the finally correct answer, then we reward every single step in the trace. So the technique we actually we rely on to achieve that is policy gradient, which is using this gradient update function. Right. So basically, if we don't take a look at the reward part, so basically this update function is moving the theta, the parameter in the model, toward the direction to more likely to make the same prediction, right? But so the key idea is how to design this reward. So we can design the reward to be negative if the final output is wrong, and we can design that to be positive if the final output is correct. So in designing so, when the reward is negative, we know that it is moving away from the original prediction in the last trial. But if the reward is positive, we will make the prediction more likely to happen in the future. Yes?
You said that everything gets penalized, but in your example, you only show 3 being penalized. So
No. I'm right. So this is confusing. I'm very sorry for that. So the 3 are the things that are wrong, but we don't know which one are wrong. So with policy gradient, we'll simply penalize everything.
Okay.
Right. So I'm very sorry to make this vision confusion to you, but actually we penalize everything here. Right. So this yes.
So is the motivation for using reinforcement learning?
Yeah.
You don't know what the sequence of operations ought to be.
Right. We don't have supervision on that.
And how long are these? How long are these typically?
So the shortest is 9 execution traces. So here in this example it has 8, but actually there will be a final in the end. So this is a simplified version of what we have, but it can run as long as over 100 or something like that. Right.
Cool. Okay. And this, how are we on? Well, I guess a question I have is there some? So you have something like 4 different operations. Mm-hmm. So if you have 9 of these in a row, you have a search space of something like 4 to the 9.
Right. So that's a very good question. So I would refer you.
Find that first good path.
Right. I would refer you.
It's more than that because the reduces have like parameters.
Yeah. There are a lot. I would refer you to our paper. We have we have 2 pages of analysis on what is the size of the search space, which is really huge. So, but in my talk, I will only talk about the high level challenges. Right. So actually, it is very, very challenging because there are 2 reasons. One is that if you simply consider the entire search space, there are only very few of them are correct. So it is very hard to actually sample the correct one in this kind of just following these policy gradient updates, right? And there is another problem is that not all the wrong traces will lead to the incorrect output. So actually, this is a wrong execution. I don't think I have time to explain that, but actually, I just tell you this is wrong, and then in the end, the finally generated answer is actually correct, right? So these are the 2 high-level technical challenges we need to handle, but actually there are a lot of very subtle small challenges.
Basic question though. I mean, the larger your input, the more likely it is you're going to start off with lots of wrong choices.
Exactly.
So you want to start with, I mean,
very good question. We actually employ curriculum learning, so that we train on the smaller traces first, and then we gradually improve that, right? So okay, so the answer to tackle these two questions is this two-phase search algorithm, which actually separate apart the instruction and the argument separately. So what it does is that on the instruction part, which we call phase one, rather than considering all the execution traces, we only consider the instruction traces, which do not care about the argument at all, right? So then in this way, if we can, right, then in this way, many different execution traces will look identical if we only look at their instruction traces. So this is a much smaller search space, which are actually manageable by the policy gradient, especially if we employ this curriculum training. Okay, so and after that, we handle the second problem in the argument part. So basically the problem that we have, the confusion we have during the policy exploration is because we can get correct for one input-output pair, but we cannot get correct for all of them. So this is when wrong execution traces happen, right? So therefore, we can simply group multiple input-output examples together to jointly train them, right? But actually, jointly train them is not a simple task, because if we don't have any supervision on all the traces, the space is huge and it's exponentially large, right? So we don't want to handle this large space. So this is why we put it in the second phase, because in the first phase we already have all the instruction traces that can lead to the correct output, right? We only need to distinguish which one is indeed correct and which one is wrong, right? So therefore, we can convert this non-supervision problem, which supervision, I mean supervision on the traces, to a weak supervision problem, where we have a weak supervision on the instruction but not the argument. So this problem becomes much more manageable than the original problem, which we have a very huge search space, right? So so these are the high-level message we have here. I will not go into the detail because we don't have time. So typical, and then I want to mention our evaluation. We developed two grammars, as I mentioned at the very beginning, and we compare a bunch of different techniques available in the literature. And then for the training data, we created two training data. The first one is the one that our technique uses, which is a training curriculum that contains only 100 to 200. Actually, it's around 150 input-output examples, which are not huge for deep learning approach. And to be fair, but actually, if you're using this only this small data set, all of them will fail, right? So it is not fair for them. So on the other hand, we create a large data set which contain not only the curriculum, but also 1 million randomly generated input-output examples, so that we can do a fair comparison with previous approach like sequence to sequence, right? So, and then here is the results. So I want to mention, so here I don't print it here, but I want to mention the training set contain inputs of length 50. I mean the randomly generated input contain input sequence of length 50, but our curriculum will contain shorter inputs. Therefore, for this test set, for the test set, we create test sets with input of length 50 and test sets with input that is 100 times longer, right? On the test 50, we observed that the sequence to sequence model and for the sequence tree model, they behave well. This is because the training length and the output length are the same, are very similar to each other. But however, when we grow into a longer input, only our approach can achieve 100% accuracy, and none of the other approach will work. So this simply shows that, as I promised you, that this sequence-to-sequence approach simply doesn't generalize to longer inputs, right? Okay.
Where does it break down? So what happens if you test
500, right. So typically we increase this, 500 is also 0, everything is 0. So we increase this into test 100. So basically everything is close to 0 already. So if we just double the length, that's a good point. We will try that. We will try that. So right, typically we just want to test these programs in different orders of magnitude. So so we don't try to find the hard cutting points, right?
I'm trying to understand like why it fails.
Right. So it's simply because it doesn't contain enough information from. Right. The neural network is kind of handling the fixed input, and then it simply doesn't. Because if you want to remember longer inputs, you need a larger set or something like that. So, right.
So are you only giving it inputs that are syntactically correct?
Yeah. We don't handle out of vocabulary. Right. Syntactically wrong cases. Right.
That's kind of an important feature of a parsing.
Right. So as I mentioned, this is an initial step toward exploring this large direction. But right, there are a lot of different issues that we need to handle in the future. Okay, any problem? Yeah.
When does your method break down?
Huh?
So at 5,000 is okay, but then if you increase it further.
Right, we can increase further, but the evaluation time is just simply longer. So actually, we want to prove that our approach can generalize to longer inputs arbitrarily, but we face several technical difficulties in doing that. Right.
Also, how stable is your training, and how sample?
Right. So it's pretty stable. So we can always get what we want. Right.
So were there inputs? I mean, how many inputs were used in these tests?
So the input, right. So that's a good question. So I think the input. I'm sorry, I forgot the concrete number, but I think it's in the order of several thousand. Right.
Were there any inputs that caused your thing to fail?
No. So our thing can always achieve 100%.
Is it 100% in every? Okay, so it's a perfect parser, basically.
Right, it's a perfect parser. So basically, we only leverage this curriculum, which is much smaller than the test set, and then we test that on arbitrarily long input, and then it will all success. So basically, for this 1 million data, they are only used for our approach. They are only used for verification because we can simply achieve 100% on every single of them.
With the curriculum.
Right. With curriculum, we are done. So for all other things, we do not need that. Right. Okay. Right. So typically for this work, we are just exploring the possible directions for synthesizing more complex programs, and then we will view this as the first step toward that big area. And then we identify several key challenges, and we develop several. We made several key observations, which enable us to develop some techniques, which can actually handle these more complex parsing task to achieve full generalization with 100 times longer inputs. Okay, so right, I'm not sure if I have enough time, but I will go very quickly through this SQLnet thing, which is basically we want to. So the problem is this: we want to have we have a database and we have a natural language. Then our problem is how can we convert that into a SQL query so that they can be queried in the database. So this has particular industrial interest because which at least I know I'm aware of many different places want to make this into product, and actually researchers here are working on this, are also working on this. So typically the problem that we have is this called order matters issue that I want to emphasize. So the very naive approach, I have mentioned that multiple times, is simply a sequence-to-sequence learning, right? So we have the input sequence, which is a natural language. Then we generate a SQL query, which can also be considered a sequence of tokens, right? So the problem here is that, so we know that where is typically a concatenation of multiple different clauses with a conjunction or disjunction, right? So in this case, the order of these clauses doesn't really matter. But in either the sequence, in the sequence-to-sequence model, the order indeed matters, and it is documented in the paper about 3 years ago, right? So how people typically handle that is use reinforcement learning. So typically they can generate different kind of outputs, different SQL queries, and then to reward them whenever the execution performance is good. But actually this solution is not very effective. So we build a sketch-based synthesis approach to avoid this order matters problem at all. So the basic idea is that we have a sketch, which is basically modeling the program domain that we are interested. On the other hand, we have this dependency graph over all the different inputs. So that we know explicitly that this column only depends on the natural language question, but it doesn't depend on another column that we want to generalize. So the key question to leverage this dependency graph, we can simply compute the probability of this simple column based on the natural language question itself, rather than depending on anything else, right? So, okay, so this is the basic approach that we call sequence to set, which means that we want to predict the set of columns, but they do not have intermediate dependency to each other. So there is a very naive way as to how to compute that is to model the thing as a neural network, which we have the column, we have the question, we can compute the embedding for each of them, and then based on the embedding, we can compute the probability. We can calculate the probability as the sigmoid output of this simple neural network. So actually here, the embedding for the question is computed using STM embedding. But actually, we found a better way is that when we compute the embedding for the question, we can always do the computation based on the column. So for different column, we should put attention on different parts of the natural language question. So therefore, rather than compute a unique question embedding, we can employ the attention mechanism to compute a so-called column attention embedding. Right. This is the simple approach that I don't want to expand too much. But using our approach, we can observe, we can achieve the state of art on the list of approach that we compare with so far, and especially this one is from Microsoft. And so we observed that actually there is another approach leveraging the grammar, which is called abstract syntax network. But actually, our column embedding can improve that approach as well. So therefore, we consider column attention as a generic technique. Okay, so and then for other efforts, I just want to mention that the two work that I'm talking about today are basically at the intersection of security programming language and deep learning. And I want to mention that I also have other work in the pure PL domain to solve security problems. And I have a lot of work on studying the security of deep learning system as well, and using machine learning to handle security problems. So I actually have a lot of slides, but I don't want to show you because I didn't expect it, right? So it's very popular. But they are just my collaborators, and I'm very happy to share with you my work. And right, I guess we don't have time for more questions, but right, maybe one or two more.
A couple of questions. Thank you.
Right.